Hello guys, so welcome back to a new VHDL lessons. We're gonna continue our combinational logic design. Okay, so we started by the half adder in the last video, and now it's time to implement the full adder. We're gonna start by the full adder structural design, in which we use what we have already. So we designed the half adder, and we knew from our lectures, our VHDL lectures, that we can design the full adder using three half adders like this. Also, this is not fully optimal, as we will see in the next video and as we saw in the lectures, but this is really easy thing to implement. Just three lines and you will have, a full adder. Okay. So as you see, guys, the full adder, adds three bits together. So here is three bits X, Y, and Z, and here is output sum and carry as well. And we see in our lectures that when you add three bits together, the maximum number of bits you have in the output is just two. Okay, so the first step to implement such design here is to have the half adder as a component, as a package that you can use in further designs. And here is the code for the package. Okay, it's really very simple code, and we explored this in our first lessons of HDL. These lessons that puts the foundation of how to implement some behavioral design, in VHDL, how to create a package, how to create a library, how to add package to a library. Okay, so here is the package code for the half adder. Here is the package name. So this keyword here, package, defines the package name, and the package name something that you can choose any name that you like. But I like to name my packages using the same name of the design half adder, then underscore package. Something meaningful, something descriptive. Then you put here the basically the entity of the half adder. If we go back to the half adder, this is basically the entity. Half adder is the name, and here is the inputs and the outputs. Then you end here the this definition using this keyword and half adder package. Okay, now it's time to compile this. So let's compile, and we should see no errors. Good. Now this is not enough. Again, if you didn't watch our previous video, you should declare some library, and you should add this new package to it. So if you watch our previous videos, so here is how you declare a library in VHDL, and this is using this command vlib. I'm just putting in for you for your reference as a comment, but basically the command is vlib VHDL library, and here is the name of the library. You can choose any name you want. Okay, then this is also a companion, command vmap, which is basically maps what you gonna create is a library that you created to some folder in your system, in your PC. Okay, and we like always to name this folder as the name of the package. So when you go to that folder, when you navigate there in your computer, you know that this folder is for my library. Okay, then the last command here is to add this new package. Okay, after its compilation, of course, it must be compiled to this library that you created. So we're gonna do that, and you can do it multiple times. That's very fine, no problem in that at all. So just copy and paste. So this adds, since you have zero errors and zero warnings, then this will add this new package, okay, to your digital component library. So let's do that. Let's check that. And you must do that as well. You must check if you are correct or wrong. So we go to D here. Here is digital component. If you open it, of course, I have many designs before. So where is our package? Our package is called half adder package. So yes, it's in here. Okay, so we are successful, guys. Okay, that's really good. Uh, let's now do another thing. Let's now go to the design itself. So here is the full adder design. Now we can instantiate this package in our design, and connect this is the full adder in that way. as we see here. Okay, so this design had three inputs, X, Y, Z. Okay, or as we see, guys, when you use this design in the binary adder, Z will be just the input carry from the previous full adder. So a meaningful naming for the Z is to call it CI, because as we learned, when we use this full adder in the binary adder, okay, each full adder will carry 2 bits from the 2 inputs plus the carry of the previous, previous full adder as well. So in real implementation, when we use this full adder, we use it in that way, in another bigger circuit, which is the binary adder. Okay. And at that time, this Z will be basically C input from the previous full adder. So you can, of course, this is just a naming. So you can just name it Z or CI, whatever you want. Okay. Since these are the three inputs, XYZ or XYC input here, as I named them. And then the output is the carry and the sum. Okay, good. Now look at this design here. This design has three instantiations of the half adder. So here I'm defining my library that I'm gonna use, which is digital components. And I am using, this package out of this library, which is half adder package. Good. So this must be written before the entity. Then in the architecture now, we need also some signals. So these are like S1, C1, C2, S2, C3. All these are internal signals. Okay, so they must be defined as well. So here is I'm defining all of them: S1, C1, and C2, C3. And then we define our half adder. So here is the definition or the instantiation, we can say, just similar to analogous to programming language when you define a class and you instantiate an object from that class. So here is half adder one, and this is a label. You can give any label to it, but this is a descriptive one. Then here you write the entity name of the design of the half adder. So if half adder is called half adder here, so you just write it in that way. Then port map, then you make a mapping between the signals and the inputs here and this design. So if we go back to this half adder design, we have XYCS. XY is the carry, then the sum. The order is very important. So the first half adder takes as inputs X and Y. That's why I have X and Y here for the inputs. Then remember, we have the carry and the sum. So then the first carry is called C1. Then the first sum is called S1. And again, here the order is very, very, very extremely important. Okay? Because this will be mapped to the carry and this will be mapped to the sum. Okay? The second half adder takes as input the third input Z or CI, as I name it here. You can name it whatever. And the first input is basically S1, okay, which is the output of the first half adder. So here is S1 CI. Then the outputs are C2 and S2. But remember, so C2 is a carry output here, but remember S2 is just the final output S. So you don't need to, to name a new signal, because basically this signal here will be basically the final output sum. So just write S here, which is our one of our outputs. In the instantiation of the third half adder, okay, this half adder have two inputs as well, C2 and C1, C2 and C1. Then the outputs are, the carry is C3, and the sum is basically the carry of the overall design. That's why I call it C here. I no need again to make another signal called S3. Okay, so that's basically the design. Just the 3 lines as we see here. Just the 3 lines. Okay, just make a sketch of your design and just follow what you have sketched here in the design itself. So let's compile this. Good. Now we're gonna simulate. For the simulation, we need a test bench. So here is a test bench of the full adder. So this is it's called version 2, because I have another version for it. As we see in the lecture, there are 3 designs of it. Good. Here is a test bench. Okay. Again, this is just a template that we follow. Here we put the entity of the design. So let's remove this now. So here is just the entity, 3 inputs and 2 outputs. 3 inputs, 2 outputs. Okay. I call here so let's call this just C, just to be match it very well. I change from time to time the naming, but that doesn't change the behavior. So this is basically the same entity as our full adder here. Okay. And we define here signals for each one of these inputs and outputs. So we have 5 signals. Okay. Then here we instantiate our design. So here we put the entity of our design, which is that guy here. And this is just a label. DUT means device under test, or design under test. This is just a label. You can name anything here. But of course, DUT is more meaningful, as I said. Then, this is also important, the order. So xn will be mapped to x, yn will be mapped to y, cn will be mapped to ci, and then cout will be mapped to c, then sout will be mapped to s. Then here, remember, we have 3 inputs, so we have 8 different combinations. So starting from 3 zeros until we reach 3 ones. And you can, after that, you can make this clearance. It's up to you. Okay. So let's now compile that also. We made some minor changes in it. Yeah, now let's simulate it. So simulate, start simulation, work. And we choose full other version 2, structure test bench. I think it doesn't work here. So we go manually. Yeah, full other version 2 structure test bench. Here it is. And we have those. Okay, now we need at least 8 nanoseconds because we have 8 combinations. Look, guys, 8 combinations because we have 3 inputs. So let's, just tick here and yeah, that's very enough. Then yes, then we do our simulation, or I'm sorry, this start simulation now from here, run for 1 nanosecond. And you can just, if you want the 8 together, so you can just make like this. This will run the simulation for 8 nanoseconds, of course, since we already run some of them. So, you have extra here. Okay, let's now check what we have. So here is 3 zeros. This will give us 0, 0 because the sum of 3 zeros is just 0. Then 0, 0, 1 will give us sum of 1 and carry of 0. Then 0, 1, 0 again will give us a carry of 0 and a sum of 1. Then 0, 1, 1 will give us 3, or I'm sorry, 2. 2 is sum of 0 and the carry of 1. And we can continue until we reach the final state here in which we have 3 ones, which is 3, 1, 1. So here is the carry is 1 and the sum is 1. Okay, guys, then here is the reset combination and we'll continue forever. Okay, guys, that was, the first design, which is not optimum, as I said, but it's really easy to design of the full other. So stay tuned for the next video in which we're gonna explore the second design, which is the most optimum for the full other. Thank you very much for watching this video and see you in the next video. Bye-bye.